Hi guys, welcome to my channel. In this video, I will explain the last three phases of the compiler, that is intermediate code generation, code optimization and code generation. Before going in detail, let me give the brief introduction. After the compiler completes the lexical analysis, syntax analysis and semantic analysis, it enters the code generation stages. These stages generates an intermediate representation, optimize the program for better performance, and finally produce the machine code that the computer can execute. Let's go into the slides and let's see in detail. The compiler faces a recap. The source program given to the lexical analysis, where it converts the character into a token. Those token is given to the syntax analysis, where it checks whether the program follows the grammar rules. Then it is given to the semantic analysis. It checks the meaning of the program such as type, compatibility and variable declaration. Then it is given to the intermediate code generation, where it creates the machine independent representation. Code optimization, next phase, it improves the efficiency without changing the output. And code generation, which converts the optimized code into the machine code. In this video we will focus on the last three phases. Let's go into the next slide. Intermediate code generation. Intermediate code generation is the fourth phase of the compiler. It converts the source program into a machine independent intermediate representation. Instead of directly generating the machine independence, compiler generated intermediate code because it's easier to optimize and can be translated into a machine code for different processors. The objectives: simplifies compilation, enables optimization, machine independence, and portability. Simplifies compilation. The intermediate code makes the compilation process easier. Machine independence. The same intermediate code can work for different computer architecture. Enables optimization. The optimization algorithms works on intermediate code. Portability. The compiler can generate the code for multiple machines. Let's go into the next representation. Intermediate representation is a simplified form of the original program. There are the several types. Three address code, most commonly used. Quadruples, which stores the operands in four fields. Triple, which is similar to the quadruples but without temporary variable names. Indirect triples uses the pointers for better optimization. Syntax tree represents the expression hierarchically. Directed acyclic graph removes the repeated computations. For example, we can see the source code A equals B plus C into D, where always top priority is given to the into. The compiler first calculates T1 equals C into D, then T2 equals B plus T1, then finally A equals T2. This is called as three address code because each instructions contains at most three address. You can see two operands and one result. Let's move to the next slide. Code optimization. After intermediate code generation, the compiler optimizes it. It improves the intermediate code without changing output. Goals, which reduces the execution time, reduces the memory usage, improves the CPU efficiency, removes the unnecessary instruction. Let's go into the next slide and let's see in detail. Optimization techniques. Constant folding. we can see the source code x equals 5 plus 3, which is tends to x equals 8. It is the machine independent optimization where the performance is done before the machine code generation. Instead of calculating during the execution, it is calculated before at compile time itself. Before execution, at compile time itself only it is calculated. Constant propagation. A equals 10. Since A is already known, the optimized B equals 15. The compiler replaces the variable with the values whenever possible. Dead code elimination. The original is x equals 5 and x equals 10 removes first. The first assignment is never used. The compiler removes the x equals 5. Only the useful instruction remains. Common sub-expression elimination where multiplication will be repeated. You can see A equals T, D equals T. Next, we'll move to the next slide. Code generation. Code generation is the final phase of the compiler, as we know, which converts the intermediate representation into the machine or assembly code. The responsibilities: register allocation, assigns the variables to the CPU register. Instruction selection, choose the best machine instructions. Instruction scheduling, arranges the instruction order for the better performance. Memory allocation, manages the storage locations. The output is executable machine code. Let's move to the next slide. A equals B plus C. Intermediate representation, T1 equals B plus C. A equals T1. Assembly code is like load R1 comma B, which loads the value of B into the register R. Add R1 comma C, which adds the value of C to the register 1. Store A comma R1 stores the result from R1 into the variable A. Finally, the processor executes the machine instruction. Let's move to the next slide. Comparison. Faces input, output, and purpose. Intermediate code generation. The input is semantic tree. The output is intermediate code. The purpose is machine independent representation. Code optimization. Input is intermediate code. Output is optimized code. And the purpose is improves the efficiency. Code generation. Input is optimized code. Output is machine code. And the purpose is produces the executable program. We'll go to the next slide. Summary. Intermediate representation is machine independent. Optimization improves the efficiency. Code generation produces the executable code. Thank you one and all. If you get any doubts, please raise your doubts in comment box so that I can respond. Thank you.